It is time for convolutional neural networks, the first major topic in deep learning for Berkeley Coding Academy. I'm excited. I hope you're excited. Let's jump right in. So, what are CNNs, short for convolutional neural networks? CNNs are the leading image classifiers in the world. They got their jump start in the famous ImageNet competition, which has been given out over the years. And at some point, CNNs emerged as the leading model, basically obliterating the competition. And they've been in the lead of image classifiers ever since. So CNNs classify images by filtering 2D and 3D patterns within an image. This is comparable to how the human brain works. We look at images in real life and we see two-dimensional representations. This is different than a one-dimensional string of pixels, which we previously used in building neural networks. So CNNs can detect high-level patterns like eyes and low-level patterns like lines. CNNs work by placing filters over images that reduce the number of pixels and transform their values. The transformation is called a convolution. The convolutions and corresponding filters are optimized during the learning process. Okay, dot product. Why is this up here? Well, convolutions make repeated use of the dot product over an image. Okay, in effect, it's a bunch of dot products. So what are dot products? The dot product is a fundamental linear algebra operation that multiplies and sums matching components. Here's an example. Consider the list 2, 3, and 1, 4. Now these could be considered two-dimensional. They could be considered points in the plane. Okay, so the inputs are two-dimensional here. And the dot product says, well, multiply the first components together. That's 2 and 1. Multiply the second components together. That's 3 and 4, and then sum them. So we get 2 plus 12, which is 14. Note, very interestingly, that this is a one-dimensional output. So dot products not only provide a transformation, but they reduce dimensionality, which is very critical when dealing with a huge number of parameters, as is the case in images and especially video. Videos also use CNNs. So let's look at a convolution example. The following filter uses a 2x2 dot product to reduce the number of pixels and transform their values. Okay, this is pretty cool. So the filter is basically the 1, 2, 0, 1, right? And what's going to happen is it's going to go over the entire image. All right, it's going to go over every group of 4 numbers. And as you can see, it results in a smaller grid of numbers because, you can't, like this is the upper left, okay? You can't go further to the left or further up. And what it simply does, it multiplies the upper left pixel by 1. So in this case, we get 1 times 1 is 1. The upper right pixel by 2. We get 2 times 2 is 4. So that's 1 and 4. The lower left pixel by 0. That adds nothing. And the bottom right pixel by 1, that's 1 times 4, so another 4. So we're adding up 1, 4, and 4 to get 9. This convolution will be repeated over the entire grid of pixels to fill out the array of numbers that you see on the right. By the way, you can call these matrices of numbers as well. Okay, consider horizontal lines. The following filter detects horizontal lines in an image. Okay, can you see why? So if you bring this 3x3 filter over a bunch of numbers, what does it in fact do? You're going to get zeros above and below, the rows above and below, but you're going to be summing horizontal pixels. That's the whole thing. It sums horizontal pixels, so it's actually going to detect horizontal lines. Consider now vertical lines, and you can think, what may a matrix of, like a filter of vertical lines look like? Well, the following filter detects vertical lines in an image. And look at that, it's very similar. So in effect, right, if you imagine just a big grid of numbers and you put that over it, well, you're going to get a bunch of zeros on the left and the right, but you're going to be summing vertical columns. A 1, 1, 1 means 1 times 1 pixel plus 1 times another plus 1 times another, but it's all in the vertical direction, okay? Similar techniques can be used to discover edges and other shapes. Now, you don't have to be concerned with the technicalities here. I'm just trying to give you an idea of how the transformations, the convolutions actually work. The machine learning model will actually randomly search and try to find the optimal convolutions for you. Now let's just take a brief look at 3D convolutions. How is that different? Well, if you want to deal with color images, which is common, then you actually need 3 dimensions because you need the red, green, and blue. And it's actually done in a similar way. Don't be too concerned about the details. It's still a dot product, and note that it does give a nice reduction here, okay? So we'll be doing both black and white images, which are 2D, and color images, which are 3D. Now let's look at something different called max pooling. What is this? Max pooling is another technique to reduce the number of pixels. Why are we always trying to reduce the number of pixels? Because the parameters can get just outrageously big with building convolutional neural networks, and we want to keep them manageable so that it's, building the machine learning models doesn't take too long. Okay, so here's a visual image of max pooling. I think it's pretty clear. Simply put, you take the maximum pixel in each of those little colored grids, right? So if you look at 1046, the orange grid there, the max pixel is 6. So in the max pooling reduction, you transform that to 6. And similarly, if you look at the green, you have a 2, 3, 6, and 8. Well, the max is an 8, and so on. So max pooling chooses the largest pixel among adjacent grids of pixels. Note that unlike the convolutional dot product, it does not overlap. Okay, the convolutional dot product is not adjacent. It'll actually overlap every 2 by 2. Okay, so this is a little different. Kind of simpler in a way. Okay, now let's look at a complete CNN. So we have an image of a robot and then a series of, you could say, transformations resulting in an output. And the output classification here could be, a certain type of image. Maybe it's robot. Maybe there are 10 different images to pick from. So let's just look at this briefly. We've got first convolutions. Now, note importantly that it's not one convolution here. There's actually multiple convolutions. And that's why you see multiple feature maps. It's just not good enough to do one, then it's just a simple reduction. But if we have horizontal lines, vertical lines, maybe like an arm detecting line, it's not a line, but a pattern, then we have like a different set of feature maps that can work together to help classify the image. Now, in the next step, when you see subsampling, that could be like max pooling. We can reduce the feature maps. We can go through another set of convolutions and another subsampling. And then at the very end, we actually do use the old trick of a fully connected layer back to the one-dimensional pixel classification for the output. Okay, but doing it like this has been shown to be hugely beneficial, meaning like you get much better accuracy. Okay, so some notes. Note there are multiple convolutions in multiple rounds. Max pooling is an example of subsampling that we will use. The final round goes back to 1D densely connected representations. Additionally, we pick the size of the filters, right? Commonly 3 by 3. There are actually even different ways to represent it, like 3, 3, or even kernel size equals 3. 2 by 2 is also commonly used. We pick the number of filters, right? So this is basically like, if you look here, the number of feature maps. It's commonly 32, 64, 128. Note that those are binary representations. You just start by 2 and multiply 2, 4, 8, 16. You could really pick anything. And then fine tuning is going to be important to avoid overfitting because, these are going to be pretty precise. And max pooling and subsampling is also a technique to cut down on the overfitting. Okay? So that is a complete representation of a convolutional neural network. It's really exciting. I think the purpose here is not to understand every detail, but just to get a general overview of kind of how they work and have an idea of what the code that we're going to execute is going to do. All right, let's do it in Colab notebooks.